Hello viewers, and welcome to another topic for today that we are going to look at. It is called the periodic table of elements. This topic is going to be very much exciting. So first we look at identifying properties of the atoms. Remember in our previous lessons when we were looking at matter in general, we talked about some of the properties of matter, and that atoms in the periodic table or the elements are made up of subatomic particles. So having an in-depth knowledge of that, the previous topic, will give you a better opportunity to further understand this topic that we are looking at today. When we are trying to identify the properties of atoms, we know approximately where to find the parts of the atoms. As I mentioned, that those are the subatomic particles. Where are the protons and neutrons found in an atom, and where do we find the electrons in an atom? And understanding those factors will help us to gain an in-depth knowledge of elements that are represented on the periodic table. Still looking at the properties of atoms. When we look at the individual atoms and yet interacting chemicals, and we are able to group them based on only the properties they present when in isolation, but also the properties they reveal when exposed to other elements or compounds. So looking at all these properties, the periodic table will give you an in-depth knowledge of the properties of elements when in isolation, and then also properties that you can predict if you want to form new compounds. Then the periodic table of elements. The periodic table of elements contains physical and chemical information about every element that matter can be made of in the universe. When we look at this statement here, there are two underlying words, keywords, that we have to look at. Those are chemical and the physical properties of the elements. These two keywords of every element. It is the periodic table that gives us those ideas. So looking at this statement here, now we ask ourselves a question. Why is the periodic table one of the most useful tools ever created by humans? Why is the periodic table one of the most useful tools ever created by humans? Now, before we answer this question, let me give you this analogy as well. Suppose that you want to watch your favorite TV show on a TV station, and this TV program, you don't know the time that it will be played. You have to, and you are very much interested in seeing that program played on the TV. So and you have other programs also that you need to attend to, and you don't want to lose either of these programs. So you can imagine how inconvenient it will be for you as an individual that is very much interested on seeing a program played on a TV channel, and then also you don't want to lose your other opportunities or programs that you have to tend to. So what will make it more convenient for you not to lose all these activities is to have a schedule, sort of a table guide that will tell you what time the program is to be aired, and you will be able to better program yourself when you need to run other programs so that you will have time to see your favorite TV show played on the channel. So again, attaching that analogy to the concept of the periodic table, when scientists were organizing the known elements, they noticed that certain patterns of chemical and physical behavior kept repeating themselves. In other words, the properties of elements, certain elements, keep on recurring even though they are different elements. And some of these properties are, for instance, when we look at these elements that are here, listed here, we have lithium, sodium, and potassium. They observe these properties in those elements, that they are shiny metals and they react violently with water. And then you also have another group of elements on the other end, which are helium, neon, argon, krypton, xenon, and radon. These elements are all very stable gases. So these are some of the things that scientists observed in those days. So still, we come back to the periodic table. These patterns were so predictable that the father of the periodic table, called Dmitri Mendeleev, he is the scientist who formulated the periodic law, and he was actually able to predict the existence of elements number 31 and number 32, even though these elements are not within the context of our discussion here. These two elements, as of that time, the time that Mendeleev was formulating the periodic law, these two elements were not discovered, but he approximated their masses. He was able to give their masses approximately before even their discoveries, based on the existing patterns of the known elements. Let's go back to our previous slide. Now, what Mendeleev actually did was, he looked at these elements here, then have seen that they display similar patterns and properties. So, and then other elements that were discovered as of that time, he was able to also predict the mass and properties of the elements number 31 and number 32, even though they were not discovered. And these elements, when later discovered, were known as gallium and germanium. So Mendeleev's work preceded the discovery of the subatomic particles. That is the time that Mendeleev was predicting these properties of these elements. Then he has no idea about the protons, neutrons, and the electrons of elements in the periodic table. So now we look at the periodic table again. Remember, we asked a question: why is the periodic table one of the most important tools ever created by humans? And I give you an analogy to that. Now, let me further explain why it is one of the most important tools ever created by humans. Because this is a table which shows elements arranged in order of their increasing atomic number. It is a table that arranges the elements in order of increasing atomic number. Now, let's take a pause for now, and then let me go back to tell you a brief history of Mendeleev's discovery of the periodic table. As of the time that Mendeleev formulated the periodic table, so many scientists have tried in trying to make their own periodic table. They failed. You have the likes of Newlands. Then you have so many laws that they also formulated, like the law of the triads. You also have Mendeleev's own version of the periodic table, and then he also predicted, or he also formulated his own periodic table, and his periodic law was stated as elements in the periodic table are arranged according to increasing atomic mass. But his law failed at element number 18 and number 19. He cannot give a genuine explanation to that, because in those two elements you have argon, which is element number 18 and it has a mass of 40, and potassium, which is element number 19, has a mass of 39. And his periodic law states that all the elements in the periodic table are arranged according to increasing atomic mass. But in these two occasions, or in these two elements, the law is not binding. So he cannot give a genuine explanation to that. So it is from his formulation of the periodic table that scientists were able to perfect the modern periodic table. So for that, we say kudos to Dmitri Mendeleev as the father of the periodic table. And now, this is the modern version of the periodic law, which states that the periodic table is a table which shows the elements arranged in order of increasing atomic mass. Instead of increasing atomic number, they are arranged according to increasing. So instead of arranged in order of increasing atomic mass, they are arranged in order of increasing atomic number. That is the modern periodic table. And the reason why the periodic table is the most important tool is because all the substances that we are able to make today are made up of atoms or elements. And these elements are found on the periodic table. And when they are arranged on the periodic table, their properties, be it physical or chemical properties, are all being determined. So that is why it is one of the most important tools that is ever created by humans. So now we look at the periodic table closely again, that it consists of groups and periods. And the groups are elements in the vertical column, and the periods are elements in the horizontal rows. We will take a closer look at that later on. Elements in the same group or period will have similar chemical properties. As I mentioned previously, looking at the history of the periodic table, this is Mendeleev's argument that element properties are a periodic function of their weights or atomic masses. I already explained that, because he believed that elements in the periodic table are arranged according to increasing atomic mass, as I stated. But we now come to realize that this statement is not true, but instead they are arranged in order of increasing atomic numbers. We now know that the elemental properties are a periodic function of their atomic numbers. Atoms are listed on the periodic table in rows based on number of protons. The periodic table is made up of rows and columns. The rows in the periodic table are called periods, and the columns in the periodic table are called groups. And groups are sometimes referred to as families, but the group is the more common term. Now, let's look at this question here. The elements in the periodic table are arranged from left to right in order of dash. A, mass. B, number of neutrons. C, number of protons. D, number of protons and electrons. So, which one is the right option here? Looking at the options that we have, which says that mass number is the correct option here. Is mass, are elements in the periodic table in order of increasing atomic masses? No. A is wrong. Option B, number of neutrons. Elements in the periodic table, did we arrange them in order of increasing neutron numbers? No. In our previous lesson, in fact, we have determined that because of the variance or difference in number of neutrons, that is what causes elements or atoms to have different mass numbers. So therefore, B option B here is not correct. Number of protons. We know that proton number or number of protons is also called atomic number, and from just recently we've seen in the modern periodic law that elements in the periodic table are a periodic function of increasing atomic numbers. So therefore elements in the periodic table are arranged from left to right in order of increasing number of protons, because number of protons is also equal to atomic number. So option D is automatically wrong, since option C says that number of protons. So now we are looking at groups. Remember, we said that elements in the periodic table are arranged in vertical columns called groups and in horizontal rows called periods. So let's look at the groups in the periodic table. And the elements in the same group have same number of electrons in their outermost shells. What that is saying is all the elements that are found on the same group, on the same vertical row, all have the same number of electrons in their outermost shell, that is in the last shell of the atom or the element. This makes them to have similar chemical properties. There are 8 groups. At this level, we are looking at the 8 groups ranging from group 1, that is Roman figure 1, to Roman figure 8, or some may frequently write it as 0, and some of the groups have special names as we will see below. So these are the main group elements. Remember, we said we have 8 main groups at this level, but looking at this periodic table here, we have up to 18 groups. What makes it 18 groups? In between group 2 and group 3 of the periodic table, we have 10 vertical columns, and these 10 vertical columns is where we have the transition metals. So this is just a simplified outline of the modern periodic table, but at this level we are not going to look at this. I just bring it for you to know that in essence or in actual reality, this is how the periodic table looks like. You have the first group, which is comprised of the alkali metals, followed by group 2 elements, which are known as alkaline earth metals. After the group 2 metals, you have the transition metals. And the transition metals are a group of 10 vertical columns. Then you have group 3, which is the boron family. Group 4 as the carbon family. Group 5 as nitrogen family. Group 6 as oxygen family. Group 7 as the halogen family. Group 8 as the inert gases. It has several names: inert gases, rare gases, or noble gases. So, but our focus now is going to be on these 4 main groups of elements. We have the group 1 elements. They are called the alkali metals. Alkali metals. Group 2 are called alkaline earth metals. Group 4 are called halogens. Group 7 elements are called halogens. Group 8 elements are called noble or rare or inert gases. So when we look at all these names that they are referred to, all have some meanings that are attached to them. Group 1 and 2, they form basic substances. That is why they are called alkali or alkaline earth metals, or alkali metals for group 1. The group 7 elements are called the halogens because they form salts, that is, they are called salt formers. And the group 8 elements, they are called noble because they feel that they are the kings of elements in the periodic table. They have an octet field or maximum number of electrons on their outermost shells. They are called rare gases because before the discovery of electrons, scientists have no idea about their outermost shells. So they don't frequently found them because of they don't oftenly combine with other elements. So the scientists thought that they are very rare, but in essence, they are actually available at that time. Inert. Inert means unreactive. They are not very reactive. The group 1 elements, that is the alkali metals, they are found on the left edge of the periodic table. They tarnish easily in air by reacting with water and its other reactive components. That is, when they react with oxygen and carbon dioxide, they usually form basic oxides. Because of that name, they are given the title alkali. And they also react with water to form alkaline solutions. So examples of group 1 elements are lithium, sodium, potassium. So we move on to the group 2 elements. The properties of group 2 elements are they are found next to the alkali metals. They are reactive but less reactive than the alkali metals. That is, they are not as reactive as the group 1 elements. The reason is that the group 1 elements have only one electron on their outermost shell, which they can easily lose. And when they lose that electron, they form ionic compounds. That is, they have a net charge of +1. Whereas the group 2 elements, they have 2 electrons on their outermost shell, and when they lose these 2 electrons, they form net charge of +2. That is, they form ionic compounds. Physically, they are harder than the alkali metals and have higher melting points than the alkali metals. Generally, they are good conductors of heat and electricity. They react to form ionic compounds, as I mentioned previously, and they react with water and oxygen to form hydroxides and hydrogen. So example of group 2 elements are beryllium, magnesium, and calcium. Now we move on to the group 7 elements. They are called the halogens or the salt formers. They are found immediately on the left side of the inert gases. That is, looking at the periodic table, moving from left to right, you have the group 7 elements as the second to last group of elements that are found on the periodic table. All except astatine exist as diatomic molecules. That is, when we find these group 7 elements, their members are found in a molecular state. That is, example, we have F2, Cl2, I2, that is, fluorine in its molecular state will exist as F2, that is a diatomic molecule, 2 atoms of fluorine to form one molecule of fluorine. 2 atoms of chlorine also join to form 1 molecule of chlorine. So because of that, they are very reactive and they always want to be stable. So they are always found in that state. We are going to explore that kind of linkage later on. They are reactive elements which gain 1 electron easily to have an oxidation number of -1. Except for fluorine, they have variable oxidation states. They are non-metals and insulators. Their reactivity decreases down the group. That is, moving from the top, starting from fluorine, moving down to astatine, their chemical reactivity decreases. So examples of halogens that exist as diatomic molecules, that is, they are fluorine, chlorine, bromine, iodine, Now we look at group 7 elements, which are called noble gases. Another name for these groups of gases is also rare gases or inert gases. They appear on the right edge of the periodic table. All of them are monoatomic gases. Monoatomic means they exist as single elements. They exist as single elements. They exist as single elements. In general, they are chemically unreactive. Because of that name, their unreactivity, they have the name rare gases or noble gases or inert gases. This unreactivity or inertness is due to the stable or completed shells. So examples of inert gases or noble gases are helium, neon, argon, xenon, and etc. So this is a representation of the groups of elements in the periodic table, starting from hydrogen. And then I did not talk about this other group of elements because it is a little bit higher than this level, but they are called the lanthanides and the actinide series. We are not going to look at the transition metals and the actinide and the lanthanide series here. So this is just a classification of all the groups in the periodic table. The ones that are in red color are called the alkali metals. The ones that are in lightly yellow color are called alkaline earth metals. So the gray color are other metals. The ones that are in gray color, that is under the boron family, moving towards bismuth here, we are not looking at that. They are referred to as other metals. So the one that is somehow sea green or so, they are the metalloids, that is half metals and half non-metals. Those are the ones that we call metalloids. We will explore that later. So between group 2 and group 3 of the periodic table is where we have the transition elements, starting from scandium up to mercury. So we have the ones in green color are the non-metals, the other non-metals. So the one in light blue are called the lanthanides. The lanthanides, starting from lanthanum right up to. Then we also have the actinides, that is in dark blue color here. Then we have the halogens in yellow color here, the halogen family. And then we have the noble gases at this far end of the periodic table. So, but at our level, this is what we are going to focus on at our level of general science. This is a simplified model of the periodic table that are listed from group 1 to group 8. So on the horizontal and on the vertical columns, that is what we call the groups. And then on the horizontal rows, that is what we call the periods. So we have group 1, group 2, 3, 4, 5, 6, 7, and 8. So we have period 1, period 2, period 3, period 4. That is where we are going to stop at this level of our science. This is a simplified model of the periodic table that we are going to stop at this level of science. So let's look at this question. What is the atomic number of the element in period 3, group 6? Now, let's get back to the periodic table here. As I talked about previously, we have the groups in vertical columns, and these are the periods here. So this atom that we are talking of is in what period? Is in period 3 and in group 6. Let's get back to the periodic table for that. This is group 6 here, and period 3 is right here. So where these two intersect, that is going to be the atomic number of the element. So that will lead us to right here. And so therefore, the atomic number of the element is going to be 16. It is 16, which is sulfur in the periodic table. So looking at the answer here, we have 16 as the answer. The atomic number for the element in period 2, group 3. So looking at this question, we have to first know how the periodic table looks like. Here we have group 1, and period 2 here. So this is group 1, group 2, and group 3. This is our periodic table here. We have this ones as a group and this ones are the periods. So here we have hydrogen here. Let's say that we have hydrogen here. The other end of the periodic table under group 8 will have helium there. So this one here will be lithium, followed by beryllium. Then we'll have boron here. So if this is atomic, this one has atomic number 1, then helium at the other end will have atomic number 2. So lithium here will have atomic number 3, beryllium will have 4, and boron will have 5. So, and the question says that what is the atomic number for the element in period 2? So this is period 2 here, and in group 3. So we have group 3 here. So where the 2 meet is where our answer is going to fall. So the atomic number of this element here is going to be 5. I hope you all understand that question. Move to the next slide. Determinants of group and period numbers. That is, now we are going to look at what determines the group number of elements in the periodic table and the periods in which they belong to. The number of valence electrons or electron that an element has determines the group number, while the number of shells determines the period number. Group number is usually written using Roman numerals, whilst period numbers are written using Hindu-Arabic figures. That is, when we want to represent the group numbers of elements in a periodic table, we use the Roman numerals such as capital I for group 1 elements, capital II for group 2 elements, and VII for group for group 8 elements. These are what we call Roman figures or Roman numerals. But for periods, we use 1, 2, 3, 4, and so on and so forth. Those are the numbers that we use to represent periods of elements in the periodic table. And how do we find group number of elements? The number of electrons in the outermost shell of an atom, as we have seen in the previous slide, that if you have an atom, the number of electrons that are found on its outermost shell usually represents the group number of the elements. That is, those elements that are found on the periodic table, for instance, those in group 1 have 1 electron on their outermost shell. That is, when we look at their last shell, they have only 1 electron. Therefore, their group number is 1. And those in group 2, they have 2 electrons on their valence shell or on their outermost shell. So they belong to group 2. So this is how we determine or we find the group number of elements in the periodic table. For example, an atom of an oxygen has 8 electrons. Determine its group number. So in solving this question here or problem, first we have to write the electronic configuration of sodium atom, which is using the KLMN shell that we are coming to explore later on. We have 2, 6. That is, on the K shell, we have a maximum number of 2 electrons, and on the L shell, we have 6. So this is telling us that the last cell of sodium atom has 6 electrons. Therefore, the group number is 6, and we use Vi to represent that. Example 2, an atom of calcium has 20 electrons. The arrangement of the electrons are as follows. That is, we write KLMN, that is our electron structure of the calcium atom, and always the K cell takes a maximum of 2 electrons, the L cell 8 electrons, M takes 8 electrons, and N cell takes 2 electrons. The outermost shell, that is N, has 2 electrons. That is when we look at this one here, that is the large shell of calcium atom. So it has a maximum of 2 electrons on its shell. So therefore it belongs to group 2 in the periodic table. Note, if an element has a maximum number of 2 in K shell or 8 in L shell, M and N cells, then this element belongs to group 8 or group 0 elements. That is, we have to take note of this. That is, for group 8 elements, it can have a maximum of 2 electrons on the K shell. That is typical of helium atom or any other element that is nearest to the helium atom, and it can have a maximum of 8 electrons either on the K shell in the case of neon, or M, a maximum of 8 electrons on M shell in the case of argon, and maximum of 8 electrons for higher noble gases. That is not within the context of this discussion here. Now we look at periods. Elements in the periodic table are arranged with increasing atomic number in horizontal rows called periods. And in the periodic table, previously we've seen that there are 18 groups, or at our context we classify or we limit it to 8 groups only, but we have 7 periods, but at our level we only stop at the first 3 periods, or the first 4 periods in the periodic table. And how do we find the period number of elements in the periodic table? When we look at the electronic configuration of elements, the number of cells of an element that an element has, or element having electrons in them, gives the period number of that element on the periodic table. Let's see, for example, here we have hydrogen, helium. They all have 1, and therefore, which is the K cell, they belong to period 1 of the periodic table. We look at period 2 elements. Examples of period 2 elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So looking at all these elements, this is how their electronic configuration will look like. For example, when we look at the K shell, this is capital K, they have only 1 cell, so therefore they belong to period 1. So any element that has a maximum of only one shell, example hydrogen. With this hydrogen, this is how the electronic configuration will look like. So it has one shell and therefore it belongs to group 1. Lithium, which is in period 2, will have 2 shells. So because of these 2 shells for lithium, of which the first shell will carry a maximum of 2 electrons and the last shell will carry a maximum of only 1 electron. So because it has 2 shells, therefore it is in period 3, as we have seen in the example here. Lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine and neon, they all have 2 shells in their electronic configuration. That is the K and the L shell. So this is how we usually represent that. This is the K shell. So we have this as the K cell and this one as the L cell. So they have only 2 periods. So therefore they belong to period 2. Period 3 elements, example are sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. They all have 3 cells each, that is Kl and M cells. So when we are to represent that, that will be like this. So we have this as the K cell, L cell, and the M cell. So because we have 3 cells, therefore they belong to period 3. Now, how do we find the valency of an element? The valency of an element is the combining power of that element or radical to form molecules. The valency of an element can be obtained from the periodic table using the following rules. That is, when we want to find the valency of an element, remember the key word here is combining power. Combining power of an element is what we call valency. It can be an element, it can be a radical. Okay? What is a radical? A radical is a charged species. It can be positively charged or negatively charged species. Here, it can be a group of elements or it can be only one element, and it can be positively charged or a negatively charged element or species. So therefore, the valency of an element can be obtained from the periodic table using the following rules. That is, all elements from group 1 to 4. Let's take note of this. All the elements starting from group 1 to group 4, they all have a valency equal to their group numbers. That is, for example, all the elements in group 1, they all have a valency of 1. Examples of elements under group 1 are hydrogen, lithium, sodium, and potassium. That is where we are going to stop at our level. They all have a valency of 1 because they all belong to group 1 in the periodic table. And those elements in group 2, have a valency of 2. Remember, we are looking at the first rule of determining or finding valencies of elements or radicals. For elements, starting from group 1 to group 4, the element will have the valency equal to the group number. So I think we are all okay with that. So let's look at the next slide. All elements from group 5 to group 8 have valencies as, that is, if you want to find the valency of any element from group 5 to group 8, we subtract 8 from the group number. For example, if we have an element in group 5 and we want to know the valency of that element, we subtract 8 from 5, which is going to be 5 minus 8. So 5 minus 8 here is going to be minus 3. So the valency or the combining power of all the elements in group 5 are minus 3. Okay, so that is how we find the valencies of elements in group 5. Those in group 6 will be 6 minus 8. That is going to give us minus 2. Minus 2. So looking at these examples here, they are realistic in the sense that, for instance, nitrogen, which is the first element in group 5, it needs 3 extra electrons for it to fulfill the octet rule. Looking at nitrogen in group 5, it needs 5 electrons. Sorry, it has 5 electrons already in its valence electron, and now it needs only 3 electrons for it to behave like the nearest noble gas. That is why we state here that nitrogen requires 3 electrons, or any element in group 5 will require 3 electrons for it to fulfill the octet rule. So the same thing also applies to those in group 6, for example, oxygen. We know that oxygen has 6 electrons on its outermost shell, so it needs extra 2 electrons for it to behave like the nearest noble gas. So this is the importance of finding valency of elements. So those in group 8, that will be 8 minus 8, which is 0. So all the elements in group 8 except for helium, okay, they will require 0 electrons for them to behave like the nearest noble gas, which is they don't need any electron. Already they are stable. So let's look at this classwork. An element has 14 electrons. Find the group, period, and valency. Another exercise, another question also is, an element has atomic number 9. Find the group number, comma, period number, and the combining power of the element. So here we have the electronic structures or configuration of the elements. And then the final question is, an element has 18 protons. Find its period number, group number, and valency. Thank you very much for your attention, and I hope we answer these assignment questions upon our next class. Thank you.